In this lesson, we are going to study composition of functions from one-to-one and onto functions. Let us begin with this first theorem. Suppose that we have sets A, B, and C such that f is a function from A to B and g is a function from B to C. The following are true. If the composition G circle F is injective, then F is injective. If G circle F is surjective, then G is surjective. What is this saying? This is saying that if the composition of two functions is injective, then we know that the first function applied is injective. If the composition of two functions is surjective, then that means that the second function applied is surjective. Take note that it is not true that if G circle F is injective, take note that it is not true that both G and F are injective. The theorem says that only the first function applied will be injective. Similarly, if G circle F is surjective, it doesn't imply that the components G and F are both surjective. We only know that the second function applied will be surjective. Let us prove the first statement. That is, if G circle F is injective, we will show that the first function applied is injective. So I already have the hypothesis here. I already copied that. So we want to show here that F is injective. Let me first write the definition of injectivity so that you know how the proof will look like. What is the definition of an injective function? That means that for all A1, A2 in its domain, if two images are equal, then the pre-images must be equal. Recall that the opposite direction is a definition of well-defined function. But this direction is saying that the function is injective. So therefore, let us proceed with the proof. So we have let A1 and A2 be elements of A, and we are supposing that f of A1 is equal to f of A2. Okay, how will we now use the fact that G circle F is injective? Remember that we want to go here. This is our goal. We want to show that A1 is equal to A2. In order to have G circle F, I will apply G to both sides. And will I be sure that this is true? Will I be sure that the resulting elements will still be equal? Yes, because G is a function. Since G is a function, when we get the image of f of A1 and f of A2, they are equal, so therefore the images should be the same. That is the reason why we can apply G to both sides. G of f of A1 must be the same as G of f of A2. Again, of course, we can get the image of f of A1 and f of A2 because f of A1 and A2 are elements of B, right? And this is what's happening. This is B to C, and this is my function G. My f of A1 are elements of B. They are equal, correct? So therefore, by definition of a function, they should go to exactly one element. So this one will go to G of f of A1. And this one will also go to G of f of A2. And they must be the same, right? Otherwise, if these two are different, then that would mean that we have a configuration like this, which is not possible for a function, this will mean that we have a one-to-many relation. Okay, so we now have this, but by definition, this is your G circle F of A1. And this is my G circle F of A2. Remember, what is it that you want to show? We want to show that A1 and A2 are the same. What can you see here? This is saying that the images of A1 and A2 under the function G circle F are the same. What can we say now about that? Let us recall the definition again of an injective function. I will make it star. So remember, we have star. Let's say this is from heart to smiley. This is injective whenever, for all elements in heart, if the images are the same, always remember that if the images are the same, then the pre-images must be equal. And that is exactly what's happening here, right? Your star is G circle F. We have this equality. This is saying that the images of A1 under G circle F and the image of A2 under G circle F are the same. So therefore, A1 must be the same as A2. And that comes from the fact that G circle F is injective. So let me write it here. Since G circle F is injective, we must have A1 is equal to A2. That's the end of the proof. Next, what we have here is that when two functions are injective, then their composition is injective. Second one is saying that if both components are surjective, then their composition will be surjective. And it follows directly from 1 and 2 that if the two functions are bijective, then their composition is, this one should be bijective. Let us prove part 2. That is, when two functions are surjective, we want to show that G circle F is surjective as well. Let us first recall the definition of a surjective function, but we will apply it to G circle F. What is the meaning of G circle F is surjective? Take note that G circle F is from A to C. Correct? When you are surjective, that means that all elements in the codomain can be expressed as the image of an element in A. So we have for all C, there shouldn't be a for all here. So we have for all C in capital C in the codomain. We want to show that this C can be written as the image of some element in A. I will write here for some. Instead of writing there exists, for some A in capital A. That is what we want to show. So for our proof, we will start with an arbitrary element in the codomain C. So let C be an arbitrary element of capital C. Let me just draw here the elements, the sets A, B, and C so that you can imagine what's going on. This is A, B, C. F is a function from A to B. G is a function from B to C. And remember that F and G here are both surjective. Okay, so we took an arbitrary element in C. So that's a small c in there. But take note here that G is surjective. What is the meaning of G being surjective? It means that we can find an element in its domain, let's call that B, such that the image of this B is this C over here. So we have B, when mapped under G, will be equal to C. So your C here will be your G of B. So we have, since G is surjective, there exists a B in capital B. Remember, G is from B to C. G is surjective means that all elements in the codomain can be written as the image. Remember that? The image of an element in its domain. There are no extra elements. There exists B in B such that my C is equal to G of B. But remember, what is it that we want? We want to find an element in capital A such that C is the image of an element of A under the function G circle F. Now that we have an element small b in capital B, we will now use the fact that F is surjective. What does that mean? What does it mean if F is surjective? We can find a corresponding element in its domain such that when you map this under the function F, you get B. Correct? Meaning to say your B here is your F of A. We can write every element in the codomain as the image of some element in A because F is surjective. So we write here, since F is surjective, B is equal to F of A for some A in capital A. Now, what can you observe about A, B, and C? Look at this one. When you apply the function F to A and then apply the function G, you get C. It only means that, or you can also look at this, C is equal to G of B, B is equal to F of A. What does it mean? Hence, our C is equal to G of B, but B can be written as F of A. And this is now your G circle F of A. So we have now shown that for every element in C, this is an arbitrary element, we can always find some element in capital A such that C is the image of A under the composition G circle F. So for the last word here, therefore, G circle F is surjective.